Happy Friday. Okay, so you guys have had a long week. I really hope you enjoyed the video of the lab. We try to make that as real as possible to you guys. I hope you enjoyed all the colors and the really neat things that you were able to see with the lab. Hope you got your lab report working and getting that done. So we're going to finish up today with some notes on energy and light. A lot of it is going to be a review of some things that you already learned in the POGL, which is great. And then I'm going to do a second video which I talk about how to do some of the problems. I'm going to give you some example problems. I'm going to work them out, okay? So let's just go ahead and get started. We ended on Monday talking about that we needed to do a new model or a revision of the wave model of light that was needed to address the phenomena, okay? So the quantum concept. So when objects are heated, they emit glowing light. These different colors correspond to different wavelengths and frequencies, okay? So when we heat them, so like when you saw in the lab, we were heating these chloride salts, okay, which had different metals in them. They were giving off a different characteristic of light, okay? If you put the glasses on, you could see how it diffracted that light into its emission spectrums, which causes it to use the prism, so it shows the different energies that the electrons are actually going at different times. Then we also use the power source, okay? So we gave energy in the form of an electric charge to some of the electrons, okay? So we're going to talk a little bit about that here today in the notes. In the 1900s, the German physicist Max Planck began searching for an explanation of this phenomenon, okay? Why is this happening when you heat different metals? Why are there different quanta of light being released, okay? So his study led him to these conclusions. Matter can gain or lose energy only in small specific amounts called quanta of energy, these packets of energy, okay? It also led him to start looking at or discovering what we call the photoelectric effect, which dealt with electrons, okay? He called these photoelectrons, and they're emitted from the surface of a metal right here. So see, when these light rays heat up this metal, you have these electrons being taken off the surface of the metal, and it's called electron emission. And you have these packets of quanta, this quanta of light being released. Okay, now we're going to look a little bit into wavelength, frequency, and how this all is related, okay? So the speed of light, which we talked about earlier, a wave moves at the speed of light, is equal to the frequency of the wave times the wavelength itself, okay? So if you're looking for the frequency, all right, then you're going to divide the speed of light by the wavelength. If you're looking for the wavelength, you're going to take the speed of light divided by the frequency, okay? Now, speed of light is always the same thing, 3 times 10 to the 8 meters per second. Now, how do we understand the energy? How much energy is given off in this photon? You're going to take Planck's constant times the speed of light divided by the wavelength, and that gives you the energy that that photon is giving off. Or you can substitute wavelength over frequency, or excuse me, speed of light over wavelength, which equals the frequency. So now you could also use Planck's constant times the frequency to give you the same amount of energy, okay? Planck's constant is a constant that he derived using several equations. We're not going to really get into how he derived the equation because that's a little further than what we're going to be discussing in our class. But if you take college chemistry, they may actually go into that in more detail, okay? Now, here you have 2 things of light here. You have your infrared laser light, you know those little laser pens that you shine, and it has a wavelength of 1,000 nanometers and a frequency of 3 times 10 to the 14. You also have green light that has a wavelength of 500 nanometers and a frequency of 6 times 10 to the 14. We're going to talk about this in a minute, okay? So just hold on to that and what I just showed you. Now, duality of light. Light exists as both waves and particles, or what we call packets of light called photons. So we call these photons because they exist in a duality nature, which means they're existing as both waves and particles at the same time. So because of that, we call them photons. Now, characteristics of waves, the speed of light equals wavelength times frequency, okay? The characteristic of photons, the energy of a photon is equal to Planck's constant times the speed of light over wavelength, or Planck's constant times the frequency, okay? So the energy of a photon is directly proportional to the frequency. That means that they're both at the numerator, okay? If they're directly related, they're going to be both at the numerator position. But the wavelength is inversely proportional to the the energy is inversely proportional to the wavelength because they are not the same. The energy is in the numerator and the wavelength is in the denominator. When you have that situation, that makes these two variables inversely related, meaning they're opposite. So that means if you have a high energy, you're going to have a long wavelength, right? If you have a low energy, I said that wrong. If you have a high energy, you're going to have a short wavelength. If you have a low energy, you're going to have a long wavelength, okay? So energy, E photon, is equal to the energy of the photon in joules. Planck's constant is equal to 6.626 times 10 to the negative 34 joules per second. And then V is equal to the frequency in hertz or seconds to the negative 1, okay? So now we're going to start going over how do we solve for these different variables, okay? So for speed of light, we can solve for wavelength by taking the speed of light divided by the frequency, or we can solve for frequency by taking the speed of light divided by the wavelength. Now for energy, it's equal to wavelength times frequency. Or we can substitute speed of light over wavelength in for frequency, giving the equation Planck's constant times the speed of light divided by the wavelength. This equation shows the inverse proportionality between the energy of a photon and wavelength. The longer the wavelength, the smaller the photon energy. Okay? So which one has the greater frequency? Infrared red light or green light? Well, longer wavelength, lower frequency. Shorter wavelength, higher frequency. And you can see how this one has a shorter wavelength. So this is going to have your higher frequency, okay? The red light, the greater the wavelength is going to be red light. The greater the energy is going to be green light. Because remember, frequency and energy are directly related. So if the frequency is greater, the energy is greater. So green light has a greater frequency and a greater energy, and red light has a longer wavelength. All right, let me check, make sure my video is doing okay. Okay, great. All right. Now, how do we calculate wavelength, frequency, and photon energy? Okay. Now, here's where it's going to get a little interesting because you're going to have to do a little converting back to metric system, dimension analysis, things like that. Okay? Here it says, what is the frequency and photon energy of the laser light used for eye surgery? So LASIK surgery, okay? If its wavelength is 710 nanometers. Now, look at your unit. Speed of light, we just went over what the equations were. Speed of light is always measured in meters per second. So we are going to have to convert nanometers to meters before we can ever start the problem, okay? So I've done this for you to show you how to do this. So there is 1 times 10 to the 9, or a billion nanometers in a meter. So in this case, I took 710 nanometers times 1 divided by 1 times 10 to the 9 and got 7.1 times 10 to the negative 7 meters. Think about it this way. A nanometer is smaller than a meter. So therefore, this exponent should be negative because this is a larger unit. If you have a small unit and you're going to a larger unit, you're going to have a negative exponent. So that's something to remember. If you did it wrong, if you flipped them, you should already know that there's going to be less in a meter, okay, when you're converting from a nanometer, all right? So now we can solve the problem. So they want to know what is the frequency and energy. So frequency is equal to the speed of light divided by the wavelength. Remember, speed of light is always the same, 3.0 times 10 to the 8, and we're going to divide that by our wavelength in meters, 7.1 times 10 to the negative 7, and that's going to give us 4.23 times 10 to the 14. Get your calculator out and do this math and make sure you get the right answer, because you need to make sure you're doing it correctly. Now, to calculate energy, so we just calculated the frequency, so now we can use this equation. Energy is equal to Planck's constant times the frequency to find how much energy. So we type in 6.626 times 10 to the negative 34, and you multiply that by your frequency, and you're going to get 2.8 times 10 to the 19, negative 19 joules of energy. And which category does this light fall into? And it falls into the visible light region. Okay? All right, so let's try another problem. Here we have the wavelength of a microwave beam is 11.5 centimeters. Then what are the frequency of the radiation and the energy of its photons? Okay? So once again, we have our wavelength in a unit that is not comparable to the speed of light. So we have to take 11.5 centimeters and convert that into meters. There are 100 centimeters in a meter. So you're going to take 11.5 divided by 100, which is the same as just saying move the decimal 2 spaces to the left, and we're going to get 0.115 meters. Okay? Then we're going to take our equation for the speed of light divided by the wavelength, so 3.0 times 10 to the 8 divided by our wavelength, and that's going to give us our frequency, which is 2.6 times 10 to the 9 seconds to the negative 1, or hertz. Okay? Now, the next part, we're going to calculate the energy. We just calculated the frequency, so now we can use this equation. Energy is Planck's constant times the frequency. So we take Planck's constant times the frequency we just solved for, and that's going to give us 1.7 times 10 to the negative 24th joules. Okay? Now, so you should have understood those problems. I will give you some extra videos on how to help you with solving some of those problems that you're going to be doing following this video. Okay? Now, the atomic spectra. This is what you were looking at when you looked through the fireworks or 3D goggles through the computer. Now, this is also from the POGLE that you did earlier in the week, okay? So when visible light passes through a prism, its components separate into a spectrum of color. White light, such as sunlight or incandescent regular light bulbs, give a continuous spectrum, which means there's no break in the colors. It's literally Roy G. Biv. All the colors blend into each other because it consists of all the colors of the rainbow, okay? So therefore, there's not going to be a break where there's going to be any lines, okay? Now, colored light, such as that from a neon sign, gives only specific colors, because you have to remember, this isn't white light. This is a specific element that is in a tube that's being energized. So what you see when you see in a neon sign, okay, and not all signs nowadays are neon. Originally, neon gas was the very first one they put into a gas tube. So that's how it got the name neon sign. So that orange light that you see, that is neon. But all of the other different colors of light that you see in those signs are actually not all neon. Okay, they're inert gases, meaning they're not going to react with anything, but they are different elements. That's why they give off different colors of light. So there is a misconception now when you see neon signs that you think everything is neon, and it's not. Neon is the orange color. It gives off that orange color. But if you take a prism or you take those firework glasses and you look at a neon sign, it's actually going to act as a prism and diffract that into specific discrete lines, which is the emission spectrum for that particular element, okay? So each line represents a specific wavelength of light, where that electron has jumped to at that point. So depending upon how far that electron has jumped in energy level will determine the color of light being emitted, okay? Because we just talked about how different colors of light have different lengths of their wave, okay, or different energies associated with the wave. So if you have a violet color, that violet color is going to have more energy and a shorter wavelength. So it's going to have to jump higher in energy levels, and it's going to emit that purple color. But red and orange, okay, will not. All right, hang on. All right, so this spectrum is produced when an element has been heated or subjected to an electric charge. Why do only certain lines appear, and what causes these specific colors of light to be emitted? Okay, we're going to go over that. Ooh, let me go back real quick. Now, I want to explain what these different things are. So, if you have mercury in a gas discharge tube, which actually we had mercury as one of our examples, and you use the prism, you're only going to see certain colors of light with mercury. Then we have strontium, and then this is neon. Neon's very bright. It's an inert gas, so you're going to see more of your emission spectrum lines in a neon than you will some of these other elements. Okay? You can actually identify an element based off of its emission spectrum, if you didn't know that, because not all elements have the same emission spectrums. They have similar colors and similar wavelengths, but they are not going to have exactly the same number of emission lines as another element. So you can actually use this to identify an element. Now, the hydrogen line spectrum contains 4 colored lines in the visible region: violet, blue, green, and red. Okay? Which color has the longest wavelength? Well, you should already know that by now, that red has the longest. Which color has the highest frequency? You should also know that. It's violet. And then which color has the largest amount of energy? Well, remember, these two are directly related, so once again, it's going to be violet. Okay? Now, this is something that should look familiar. You did this when you did the POGL, right? So the hydrogen line spectrum contains 4 visible lines. What's happening here is there's a short jump from 2 to 3, okay? So from 2 to 3, it's going to give off red light. Remember, the more energy, the further it's going to jump, okay? The more energy, the higher the frequency. The higher the frequency, the shorter the wavelength. So that's violet. So violet's all the way over here. So you can see that for violet, it's got to jump from 1 all the way to 6, the 6th energy level. That takes an incredible amount of energy. So if it's going to take that much energy for an electron to jump from 1 all the way up to 6, you're going to have a color of violet that's being emitted, because what happens is when this electron falls back down into where it's going to be, into its original energy level, then it's going to give off light. That's a lot of energy it has to give off, so it's going to give off that higher amount of energy, which is a violet color. The blue goes from 1 to 5, green goes from 1 to 4, and then 2 to 3 is going to be your red, okay? Now, Max Planck first hypothesized that energy produced by atoms can only have certain values and is therefore quantized. That's the reason why only distinct lines are seen in the element line spectrum. Energy is quantized and can only exist at certain wavelengths, okay? Now, Niels Bohr, he was a student of Rutherford, studied the line spectra of the hydrogen atom to try to understand the electrons in the nuclear model. Bohr came up with a planetary model, which we know about, in which electrons orbit in circular paths. Now, we all know that that's not the way it is nowadays, but his idea was right for the hydrogen atom. But then when we started looking at other atoms, there was some more things that needed to be considered. So they had to revise his model, okay? Now, the electron in the hydrogen atom can occupy a specific orbital. Its energy increases as the distance from the nucleus increases, which we just talked about, okay? Now, once again, same picture. These energies are jumping, okay? The transitions to lower energy levels result in the emission of light. You've got to get rid of that energy somewhere. So it actually emits that energy in the form of light, which is energy, okay? When the electron moves from a higher energy orbit into a lower energy orbit, it loses electron equal to the difference in energy between the orbits. So if you take the higher energy minus the lower energy, you're going to get the energy of that photon, which is going to give off that specific color of light. The energy released is released as a photon, okay? So that's going to be your color that's being released, all right? So which transition results in the emission of light with the greatest photon of energy? Well, that's going to be from 2 to 6, right? The biggest jump. The longest wavelength is going to be your shortest distance, from 2 to 3. And the highest frequency is going to be from 2 to 6 as well, because frequency and energy are directly related. Okay, deficiencies in the Bohr model. The Bohr model explains only the hydrogen atom. The more complex model was needed to describe all atoms in general. And then the Bohr model did give insight into the quantized behavior of the atom that was later better understood. I hope you enjoyed the lesson. There'll be more I'll give you in a little bit.